So, today I'll be talking to Kumar. Sai is a wicked smart recent graduate, slowly making a name for himself in the wider world of tech and AI. He's an incoming machine learning engineer at Canva, but made his first fortune selling Genshin Impact exploits as a kid. Recently, he published his thesis, Bias Modeling and Mitigation in Diffusion Models, as part of his honours in data science. And you can read more about him and his work on his personal website, saikumarmk.com. Or if you're in the Sydney area, he'll be presenting at SIGGRAPH Asia very soon in December. Before we cover your work in bias modeling and mitigation, let's cover Stable Diffusion itself.
Sure. So for the unfamiliar, Stable Diffusion is basically turning text to image. So you give it a description similar to how you were to imagine something in your head, say an apple falling from a tree. You say apple falling from a tree, and then the model, doing its magic, turns it into, this tree and an apple falling from it. In short, there are three driving components for the Stable Diffusion model. So there is the text encoder. So obviously humans use natural language to communicate. We can't use this to talk with computers. So we have to embed this into something similar to a vector space. So a word, say queen, is mapped to this vector. And the word king is mapped to a similar vector. After that, our task is to really turn random noise, because we've got to start with a random image. So this is random noise, just dots and dashes, has no value, looks like random nonsense, and turn it into our image, which is that apple falling from the tree.
Why have you chosen that image in particular?
Why did I choose that? It's probably because of Newton, apple falling from the tree. Yeah.
Physics nerd.
Yeah. There is a distinction here because we're talking about latent diffusion. So there's actually two categories of diffusion. So there's regular diffusion and then there's latent diffusion. Latent diffusion models do this thing where they go to a separate space. So imagine compressing your images into this thing called a latent space. So you turn it into a more limited representation. So you have your input X, and it turns into this squashed latent Z. So if you have a 512 by 512 image, it turns into a 64 by 64 latent. This thing here is called an encoder. The thing here decodes it, so it returns it or decompresses it. So what we're really doing with latent diffusion models is that we're actually doing the denoising process here. This process here is called denoising, where we remove noise gradually from the model using the assistance of the text embedding to get to our final desired output, right? The decoder here, which is part of this thing called a variational autoencoder, will turn that latent that has been denoised into our final representation, right? So that'll be, our final image here.
And why is it called a variational auto?
Variational, yeah, good question. So this is where things get interesting. It turns out that this is a task of compression and decompression. So you have a task which is to compress some data into this lower dimensional space and then recover it. The simple solution to this is to just learn the data set. Exactly. You don't want to do that. These things are standardly called autoencoders. They're typically deterministic. However, when we start adding sprinkles of random noise, so we sample it from like a normal distribution, that means we add noise to our input. So it's like X plus some amount of noise. We call this epsilon. So epsilon is, distributed normally. So it's usually some sort of Gaussian noise, right? You're adding in this random noise. That's where you get this variation.
Right. So and the V stands for, it's not a deterministic.
Yeah,
coding.
exactly.
You're introducing.
You're adding in noise. You're sprinkling noise, right? So the idea of diffusion, you're starting with this image, right?
Add in an apple as well.
Color in the apple. What we do is at each iteration, we add in a gradual amount of noise. So after this iteration here, your apple and tree are basically becoming a gradually eroded. So it's getting eroded by noise. So this is one timestamp.
That would be like t equals 0.
Yeah, exactly.
T equals 1.
You keep going until it's completely noise. The idea is that at some point it'll become identical to, you sampling from a random distribution and
just pure
noise. Exactly.
Yeah.
Right? So this is called forward diffusion. This is easy to do. You just sprinkle noise onto the image, right?
Yeah. We thought it was important to clarify what we actually mean when we say add noise to an image. One might expect that in order to go from here to here, you simply generate some noise and then add it over the original image. But it's not actually this simple. The diffusion process is modeled as a Markov chain, where the next image in the sequence is some random variation of the pixels in the current image. This is actually what causes the noise. In other words, you build a Gaussian distribution and then sample from it in order to get the next image. This is why it's called Gaussian noise. It's easier to think about a single pixel. First, you map the intensity of this pixel to a numerical value, and then build a normal distribution around it with a mean equal to that value. So if we extend this process to every single pixel in the n by n image in parallel, the next image in the sequence is sort of like just a single observation, a single point on some n by n dimensional normal distribution. Now, there's one more parameter that we haven't considered, the variance of the normal distribution. This parameter is actually predetermined and allows us to control the progression of the diffusion by specifying the variance at each step. For example, you might want the diffusion to start very gradually and then ramp up towards the end. Moreover, we said that the color of the pixel maps directly to the mean of the normal distribution. In practice, you actually scale this mean down a tiny bit in order to counterbalance the introduction of noise. Finally, I wrote a Python script which simulates this whole process so that you can see how each sequential image becomes more noisy. What you can hopefully see is how noise isn't really added, but more introduced by this resampling process.
But the interesting aspect of this is going backwards. And because you can start with random noise and ask it to step by step try to predict the noise here and remove it. So, it's like 2 is equal to image 1 plus noise.
Plus noise, right.
Plus like epsilon noise, right?
Yeah.
Your goal here is actually to figure out what the noise is. So backwards diffusion is trying to revert it.
And so is backwards diffusion stable diffusion? Like, is that...
Basically, you get to this bit here where you're trying to go backwards and try to recover the image, right? That's done by, this objective where you have the actual noise you've put onto the image minus the predicted noise. You want to minimize this. So this is your error function. You want to minimize the distance between the actual noise and the predicted noise. So you do this by training up a model that figures out how to reverse that. One last bit is these models can be guided by text. What you do is with that unit, right, you can hook in attention mechanisms.
It's always attention.
Yes,
Always
exactly.
attention.
Turns out attention is a really good way to encode relations between concepts. You do this thing called classify-free guidance that basically guides the noise towards a particular direction. So you have your prompt, call this your prompt, being hooked into the unit, so as attention layers going into it, and then next iteration, the noises.
And when you say unit, are you referring to just any neural network?
So the unit is this special type of residual network. So we commonly call those a ResNet. We use these for image processing. The unit was designed for medical image segmentation. What I mean by segmentation is, say, you have X-ray scan of someone, blah, blah, blah. Something like this.
Poor guy.
Guy. You have like their ribs and stuff, right?
Yeah.
And cutting out certain bits that belong together.
So like segmenting the anatomy of the X-ray.
Sorta, yeah, basically. Yeah. Meta has a segmentation model that can like basically cut out anything from an image.
So it's like the zoom blur feature. That's probably
basically
very lightweight model.
Exactly. Those blur models are pretty easy because all it has to do is focus on a subject, right?
Right.
The ResNet is itself just a model that does something called a skip connection. Basically, you have this thing here, feed forward layers, right? And then you have this thing called a skip connection. What this means is it basically lets you pass down data and enables you to have deeper logging connections in the network, lets you retain more information in the network. So all of these things come together and you finally have stable diffusion.
And you get your apple falling from a tree.
Apple falling from a tree, exactly.
What actually happens under the hood when I feed to the model the prompts, generate an image based on the lyric, and every girl I ever talked to told me you were bad, bad news? How does it know which parts of the sentence to extract, which like parts are relevant and valuable signal to like the end image? Obviously this is an intentionally very vague prompt, like a human wouldn't know what to do with this, right? But talk us through what actually happens.
Sure. So when you look at like the common words like and, I, stuff like that, like it's referring to a subject here. Even though we can't turn this into an image ourselves, we can make out what's going on in the sentence, i.e. the subject of the sentence. And I, so obviously this is in relation to two people, right? There's implicitly two people. And the girl here, there's another subject here, me and you, right? There's these implicit subjects, right? The attention mechanism basically relates parts of the sentence to each other, right? That's why context matters. As for what the image in itself may be, so girl, that will definitely render in the image. What the quantifier to this girl may be, so what the image may be modified into, would probably entail bad, bad news. Funny thing is that if you were to repeat words in Stable Diffusion, there are a few vocabulary hacks and punctuation things you can do. You can do bad with like several brackets, right? It really emphasizes it. Similarly, if you were to repeat something, it does get more focused on that.
Right. So that's like a sort of a jailbreak in a way, like adding
exactly.
Actual, like brackets.
Yeah. So here's the thing with the text encoder. It's a type of model. In this case, it's a clip text encoder. I guess you could say a cousin of a GPT model. They all have been trained using the same set of transformer mechanisms. In this case, it's image, text pairs. So it's conditioned on image text pairs.
Right.
Obviously, this could come from captioned images. It could come from, data sets. Image nets, exactly. Stuff like that. Anything that has image and description, it will use. Anything that has the connotation of bad, bad would likely crop up in this context. Bad could take on many meanings. It could refer to criminal. It could refer to bad grades.
There's probably a lot of like images labeled with bad. It's such a
exactly
common word.
So that's the thing when it comes to common words. Obviously, because we're sampling from a random distribution, there's still noise. It could be anything.
Would it inform the noise, or would it inform the way it decodes the noise, like in Stable Diffusion?
So it informs the way it decodes the noise. The noise is just randomly sampled. As you start to denoise it, it will push it in a certain direction, because you could denoise it one way, ask it to remove these pixels. But it may be less aligned with what the user wants, right? Obviously, this is a nonsensical prompt because it doesn't really describe a scene.
Nothing concrete.
Yeah, exactly. But it'll still try to work towards things that hit the attention mechanism.
Quickly, we're going to move on to some of the different image generation models that we have at hand today. So there's ImageGen by Google, there's Midjourney, and then of course there's DALL-E by OpenAI. On the left we have crappy DALL-E, and we have Midjourney on the right, obviously prompted with the exact same text prompt. Like, why is this model better than this model?
Okay, so DALL-E is on the left and Midjourney is on the right. Which version of DALL-E we're talking about? There are 3 iterations. And they are very different.
Very different.
Yeah, exactly.
In terms of like architecture?
Architecture, exactly.
Cool, okay. I think it was recently.
It looks like DALL-E 2, I think. Some of these models here have different architectures. Most of them are diffusion based, so pretty much all of these are diffusion based. There are suspicions that Midjourney is a stable diffusion model. Stable diffusion is open source. You can take it, modify it, personalize it, create your own checkpoints. So you can like make hyper networks, LoRa's, All these things refer to basically injecting your own character or concepts into Stable Diffusion, which is very good. Like for open source, you can't do these with ImageGen. It's not even
Not
open source, right?
Yeah. Is this sort of like fine tuning, or is it a?
It is
thing?
fine tuning. All of these things are different variants of fine tune.
Yeah.
A lot of my work was around fine tuning,
Right.
but yeah.
Yeah.
Midjourney, basically, they do a bunch of research techniques and a lot of cutting edge work on Stable Diffusion, and they basically customize it to the extent that it produces really, really good results here. Customize the living hell out of Stable Diffusion, right?
So when you say customize, are you saying that the actual training sets for both of these models was probably not that different, or not?
They're not that different,
right? But this is just
in the case of DALL-E 2, it is also a diffusion-like model. Honestly, when it comes to it, they were probably trained on a lot of data, and that is one crucial aspect here is amount of data trained on. More data is good, always. In the case of DALL-E 2, it was designed as a general model. It doesn't have anything specific for it. Midjourney has a crap ton of modes that have been specifically made for that purpose. So,
right. So you're saying this is actually a very like fine-tuned.
Yeah, exactly. So this is probably fine-tuned on a different range of styles, right? You got the realistic here. They have different cartoon modes, anime, blah blah blah.
I see.
Whereas DALL-E is more general. I haven't talked about ImageGen, but in the case of ImageGen, they use a much, much bigger text encoder. So there's the three components I told you about, right? The text encoder, the UNet, and the VA. ImageGen, from memory, is a pixel diffusion model. So it diffuses directly on the pixels instead of a latent space. Google uses T5 FLAN, general use text models. And that can go up to 540 billion parameters.
Jesus. Yeah.
And that is, I think, 20 gigs, the one they plugged into ImageGen. It's noted that there was an increase in image quality by a lot. That's what the kind of key difference here is. The text understanding of the model is actually pretty crucial. The more it has an intricate understanding of the text space, text and image, the better images you'll get. Yeah.
So you're saying like the factors that, go into determining the quality of the output, the text encoding, or the quality of the text encoding, the data set, but not so much, and then
how fine-tuned it
is.
Because you could train it on a specific style, right?
Yeah.
Whereas DALL-E doesn't attempt to do that naturally, or in the case it's been trained on a broad set of styles, right?
Yeah.
It's not as good as doing like one style in particular.
Just very quickly, could you explain how do we actually quantitatively evaluate them?
Okay. How do we evaluate these models? Well, typically called user alignment.
User alignment. And it's just like, how well does this match what the
exactly,
human being wants?
Right?
Yeah.
So there are several metrics, like object counting, right? Now, how do you count the images of objects in the image, right? Turns out you can use these things called multimodal vision models. So in particular, I've used Blip once to ask questions about an image. So you have an image, blah, blah, blah. And you could ask it, what is the weather? And it'll give you the answer. So these also use similar tech. It actually uses the clip image encoder, which is, I guess, the pair. It's like the twin sibling of the text encoder that's used. Another thing is user testing. So, user tests. Do they prefer this over another model?
So like a human being sitting there.
They do a study. And the other one is the Frichet Inception.
What the?
Distance, which is some really complex measure. It's a lot of probability theory. Basically, how close is it to, so you have synthetic images, which I refer to, and you measure it to real images, how far is it? Back in 2015, that was when image generation was actually starting to slowly take off. Like, it started generating 256 by 256 pixel images. They were barely visible. ImageGen, DALL-E, all have a FID of less than 10 from memory.